It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on energy geotechnics, which will be delivered by Professor Marcelo Sanchez and Dr. Fleur Loveridge. Fleur has over 20 years of experience in civil engineering covering both industry and academia. Fleur graduated from the University of Oxford in Earth Sciences and the University of Leeds in Engineering Geology before spending the best part of a decade as a consulting engineer for Babty Group and Mott MacDonald. During this period, Fleur's work included investigation, design and construction supervision for a variety of infrastructure projects and applied research and development in engineering geology and geotechnical engineering. In 2009, Fleur returned to academia and completed a PhD in the thermal performance of foundation piles used as heat exchangers in ground energy systems at the University of Southampton. In 2013, she became a lecturer in geomechanics in Southampton before being awarded a 5-year research fellowship from the Royal Academy of Engineering. She is currently an associate professor in geostructures at the University of Leeds. Fleur is a chartered engineer and a chartered geologist. She was a contributing author to the Ground Source Heat Pump Association Thermal Pile Standard and is a member of the International Society for Soil Mechanics and Geotechnical Engineering Technical Committee on Energy Geotechnics, TC 308, where she leads the Task Force on Energy Geostructures.
Thank you very much for the invitation and the opportunity, and thank you also to people who have signed in from all around the world, stayed on after work, or if you're in Europe like me, got up early in the morning. It's really appreciated and great to see the interest in energy geotechnics because it's going to be an important area in the future. As Marcelo said, I'm going to focus on one particular area with respect to energy geotechnics, and that's going to be energy piles, which has been a topic of increasing interest in the last 10 years or so. And I'm going to look principally at the thermal behavior of energy piles. So what I'm going to cover is a bit of an introduction to the energy challenge, particularly about heat, an introduction to energy piles, their construction, how they behave thermally in the big picture, and then look specifically at the temperature changes that occur both in piles and in the ground around piles when we use them for heat transfer and storage. Try and give some kind of tips for design, if you like. And then before concluding, I just want to say something also about in situ testing, because that's something that geotechnical engineers might get involved with in practice. So really, as I said, my focus is going to be on the thermal aspect, how we can relate how much energy we can get out of an energy pile to the temperature change that happens within and around the pile, because we need to control those temperature changes and make sure they're not excessive. Along the way, I'm going to try and kind of highlight the key issues that geotechnical engineers should be aware of, as well as where perhaps we need to learn some more. What I'm not going to talk about is the classic geotechnical design under the additional thermal stresses and strains that might result due to those temperature changes. I'm not going to do that for a couple of reasons. One, there are many people much better qualified than me to tackle that. It's been an active topic of research and recommendations for practice, but also I believe that as long as your system is operating within reasonable temperature limits, this should not be a big issue. Yes, it's something you need to think about and take account of, but as long as we have sensible temperature limits, i.e. we get our thermal design right, it shouldn't be a big problem. The only proviso on that is it depends on the soil type. So if you have very soft, kind of under or normally consolidated soils that could be susceptible to thermal collapse effluent, then that's a different issue. But for more typical soil types, it shouldn't be an issue. And I will say that some of the things in terms of construction practice and energy data might have a bit of a UK focus, but I hope that a lot of the theoretical stuff is going to be pretty applicable worldwide. So moving first of all into the kind of the heat energy challenge. Now, last year, our government in the UK was very proud to tell the world that it became the first major economy to make it a kind of a legal requirement for us to achieve net zero carbon emissions by 2050. However, like even in just the last 2 weeks, it's been on the news that both Japan, South Korea and China have also made similar commitments. So this is a quite important topic on the agenda at the moment. Now, in the UK, we've been making huge progress in decarbonising electricity. On this chart on the right, we've got emissions, grams of CO2 per kilowatt hour against date. And this red line here is the carbon intensity of our electricity grid. And you can see that it's more than halved in the last 10 years. So we made great progress on decarbonisation there. However, a lot of the energy we use isn't electricity. So actually 40% of UK electricity consumption is heat. And that heating for heating buildings, offices, homes, etc., that's a fifth of our carbon emissions in the UK. So it's a pretty important area to tackle. And also the majority of that heating comes from direct burning of fossil fuels. Now, in the UK, the carbon intensity of direct burning of fossil fuels is this kind of purple line on this chart. So you can see already that even just using electricity directly for heating is going to be better now than burning gas directly in carbon terms. But actually the electricity grid carbon density is due or predicted to decrease further in the future, which means that further electrification is going to be one of the key routes to decarbonisation of heating. The other option is shift to hydrogen, but the reality is we're probably going to do a bit of both. Now, if you electrify your heating and you use a heat pump with an efficiency of 3, then you get even lower carbon emissions. So this is one of the key technologies that we need to be using in the future if we are going to hit our decarbonisation targets. So again, just for a UK case, this is what one decarbonisation of heating scenario might look like with a bit of hydrogen and a bit of electrification. And there's a lot on here, but I'm just going to focus on a couple of things. 19 million heat pumps installed to homes. And in order to supply the extra electrical demand for moving some heating to electricity, but also the electricity required to produce hydrogen, we will need to double the total UK electricity supply and almost 3 times increase its capacity. So really big challenges that have to happen for us to hit these decarbonisation targets. And also, these are things that people are going to notice, right? So if you're in your home or your office and the electricity grid becomes greener, you just keep doing the same things, but you're burning less fossil fuels, you producing fewer emissions. But actually, to make these changes for heating systems, we have to change what happens in our buildings, and we notice. So it's going to be a big challenge. But electrification via heat pumps has to be a big part of that, solving that challenge. I'm focusing on ground source heat pumps because they have a higher efficiency than the alternative, which is air source heat pumps. Ground source heat pumps, essentially, you have a ground heat exchanger, typically a borehole, but it can be a shallow system where you embed pipes in the ground and circulate fluid through them. And that allows you to transfer heat to and from the ground, as Marcelo was explaining. Now, in some parts of the world, it's a very established technology, particularly in Scandinavia. But in the UK, we've kind of struggled to really get off the ground with significant ground source heat pump systems. The capital costs of drilling deep boreholes has been one of the issues. We also haven't quite got subsidies right to kind of increase the competitiveness. What we also found is in the early days of installing ground source heat pumps in the UK, perhaps the skills weren't sufficient in the market. So there was a bit of an image problem associated with schemes not working as well as they should have done. And also, if we're really going to hit those millions and millions of ground source heat pump systems we need, we probably don't have enough drillers, enough drill rigs, and things like that. So we need to do something to reduce the capital costs of making the ground heat exchanger and the skills in the market. And one of the ideas that we've been pursuing is, the construction industry digs holes in the ground all the time. Why are we making all these special purpose ground heat exchangers when we could be utilizing all the excavations that are already made for different purposes? And this should reduce the cost of shallow geothermal energy ground source heat pump systems. Now, there are many ways you can do that. And our research is looking at all sorts of them. But what I'm going to talk about today is just energy piles, because that's the most common application. So an energy pile is where you take a normal pile and you embed plastic heat transfer pipes in it, and you connect it up to your ground source heat pump system so that you can exchange heat with the ground. You can store heat there in the summer when you're cooling your building, and you can take it out again in the winter when you need to heat it. You can convert any type of pile pretty much to an energy pile. There are some examples in this sketch here of small precast driven piles, either square precast concrete, or you can have hollow concrete driven or steel driven, where the pipes go in the center and they're probably grouted up afterwards. In the UK, the main two types of energy pile are either bored or contiguous flight auger. Depending on the construction technique, you often end up with different arrangements of pipes, and I'm going to cover that in a moment. In other parts of the world, spiral coil heat exchangers have been more common, where you actually wrap the pipes around the cage rather than installing them vertically. This only works well where you don't have to splice the cage, so that you can attach all the pipes well in advance of installation. A traditional borehole ground heat exchanger is quite small in diameter, and you can typically only get 1 or 2 pairs of pipes in there, whereas one of the advantages with piles is they're much larger. You can get many more pipes in, and as you'll see in a little bit, that increases the energy efficiency. And as I mentioned, it should really reduce the capital costs because you're building the foundations anyway, so there's no special purpose drilling. However, the only thing you need to think about is checking what the thermomechanical implications are on the geotechnical design. So just to look quickly at the two main sorts of energy piles I've typically worked with and are most common for UK construction. First of all, rotary board energy piles. When you're making a rotary pile, obviously you're drilling and casing and typically hanging the steel reinforcement cage off the casing. You then have two options depending on whether your steel cage is in one section, whether it's going to be spliced on site. Ideally, if your cage is only in one piece, you should be able to prefabricate your heat transfer pipes onto the steel cage in the factory and have no impact on your construction program at all. You just put the cage in the hole as normal and fill the concrete. If your cage is going to be spliced on site, then typically it's easier to fix the heat transfer pipes to the steel cage on site as the cage goes into the hole, which adds a little bit of time, but shouldn't be too much of a program issue if done carefully. Probably the only thing to think about is that for some building projects, depending on the bending and shear force requirements, the cage may not be full depth in the pile, but really you want your heat transfer pipes to run full depth to get the maximum energy. So you can see in this solution here, there's like a little mini cage at the bottom to make sure the pipes can go to the base of the hole and there's enough weight to hold them down there. Now, the alternative to rotary board piles is CFA piles, or auger pressure grouted, as they might be called in the US. In this construction, obviously, you are augering under the grout, and the steel cage gets plunged into the grout or concrete afterwards. Now, if your steel cage goes the full depth of the pile, again, you can fix your pipes to the steel cage and just install them together as per normal. However, in a lot of building projects, the cage is not full depth. And so therefore, if you want your pipes to extend full depth for maximum heat transfer, you need to separately install the pipes on a steel bar, which is what you can see happening in the left picture. And then you get this arrangement of pipes here where the heat transfer pipes are in the center of the pile rather than round the edge, which you would get for a typical rotary construction. And probably because CFA piles are used in kind of city centers where you need a quieter construction and maybe your piles aren't that deep, that's probably the most common sort of energy pile constructed in the UK. And I think it's important to say that these energy pile solutions do work in terms of delivering energy, right? So this is some data of seasonal performance factor from some German energy pile schemes. So seasonal performance factor is basically a measure of the system efficiency. It's a ratio of how much heating energy is delivered compared to how much electricity you have to put in to run the heat pump and maybe the circulation pumps. And you really should be trying to achieve about 3. And in these German case studies, there's 1, 2, 3 buildings monitored over a number of different years. They pretty much all hitting that seasonal performance factor of 3. So you really are getting a successful energy system. These systems do work. And the other way to point out that they do work is to show some data from temperatures measured within energy piles from a site we've been looking at in London. And the reason I want to show this is just to show you that the range of temperatures here are really not huge. So we're looking at 10 degrees and maybe 25 degrees of maximum. And this is a relatively balanced system. There's a similar amount of heating and cooling being done in the building. It's a mixed use development. The cooling happens at higher power. So there's perhaps a little bit of heating of the ground over time here, but not very much. But the main point is the temperature fluctuations are not large. So these should be easily dealt with in terms of a geotechnical design and shouldn't need to be a big concern. Okay, so I move on to talking about thermal behaviour. I think you're starting to see already why thermal behaviour is potentially important, but essentially what we're interested in knowing is how much energy can we get out of the ground, right? But how much energy can we get out of the ground whilst maintaining these reasonable range of temperatures that aren't going to affect our primary structural function of the piles or the safe operation of the heat pump. So we want to maximize the energy for the length of pile we're going to construct anyway for our building within specified temperature limits. Clearly, we don't want to freeze the ground. We don't want to heat the pile so much that the range of temperature changes affects geotechnical performance. And also, we don't want it to be too hot because that affects the efficiency of the heat pump system as well. What we tended to do when we work in this area is draw on established methods of design for traditional ground source heat pump systems that operate with borehole heat exchangers. And I'm going to show in the kind of main chunk of this presentation how we can do that, but also what some of the issues are we need to think about, what some of the differences are when we work with piles. So when we think about the thermal behavior, it's very common to separate that thermal behavior into what happens within the pile and what happens within the ground around the pile. So in the pile, we have a number of pipes with a temperature in the fluid TF, then we have the pipe, and then we have the concrete, and then we have the ground, and the temperature, the interface between the two, I'm going to call TB, and lambda is the thermal conductivity of the respective materials. What we're aiming to do is develop a relationship between the energy we're transferring, usually expressed in terms of power, so that's watts, the relationship between that heat energy transferred and the temperature change of the fluid that's circulating in the pipes. And as I said, we typically do that by separating the two parts of the problem. So first of all, we try and work out what temperature changes are happening in the ground. Can we evaluate this TB? And we do that transiently by solving the diffusion equation in the ground. And then we say, okay, what's the temperature difference between the fluid here and the edge of the pile? And we traditionally in ground heat exchanger design, this is done by assuming a steady state is in operation. So we're looking at a constant temperature difference between the temperature in the fluid and the temperature at the edge of the pile. Once we've calculated those two things, we can sum those temperature differences. We can use spatial superposition to determine the actual fluid temperature circulating in the pipes, and therefore make sure our system is operating within reasonable temperature limits. So we can express this as follows. The change in temperature of the fluid is the change in temperature in the ground and the change in temperature across the pile. And as I said, to get the change in temperature of the ground, we solve the diffusion equation transiently. And I'm not going to give the diffusion equation, but essentially it's analogous to the groundwater flow equations, except we're dealing with variables of heat flow and temperature rather than groundwater flow and head. And our parameters are thermal conductivity and thermal diffusivity. So we can write that the temperature change that happens in the ground is related to Q, which was the heating power in watts that we applied, the thermal conductivity of the ground, and then a function I'm going to call G. And that function is related to the time that's elapsed and the radial coordinate from the center of the pile. And because we're interested in evaluating this temperature at the pile edge here, TB, we can write that temperature where the function G is evaluated at R equals RB. So that's what's happening in the ground. And then across the pile, we think in terms of a thermal resistance. So we say the temperature change across the pile, which is the difference between the temperature of the fluid and this TB at the edge of the pile, and it's equal to Q, the heating power, times the thermal resistance RB. And that covers all the temperature changes that are happening here from the fluid where we have convection through conduction in the pipe, conduction in the grout to the edge of the pile at this point here. And that's the part I'm going to deal with first. We'll talk first about what's happening in the pile, and then we'll talk about what's happening in the ground around the pile. So what's happening in the pile? First of all, I need to explain the concept of thermal resistance. So when you take the temperature difference across any structure or any material, when a unit of heat energy flows across it in a unit time, you can write this expression here. So the temperature change is Q divided by the area times the resistance. And really resistance is the inverse of conductance. The higher your resistance, the higher your insulation and the poorer a conductor the material is. And it's a steady state parameter. That's a really important point. Now, in piles, we tend to be working with small q, which is actually watts per meter rather than watts, because we do everything on a unit depth basis. And so instead we write an equation like this. So the temperature change is little q times the resistance R, where R has slightly different units here, but the concept is the same. So the pile resistance, we're calling that RB, is a function of the thermal conductivity of the concrete in the pile geometry, so like its size, how many pipes are installed and where they're installed, etc. And we try and calculate this analytically if we can to make our life as easy as possible. The equation would look something like this. I've put bars on top of the temperature of the fluid and the temperature at the pile edge to represent the fact that they're averages. So actually these are not constant values, as we'll see shortly. And then because resistance in series are summative, you can say that the resistance of the whole pile is the resistance of the concrete part plus the resistance of the pipes. And even the resistance of the pipes we can split up into the convective and conductive resistances. And those parts for the pipes are they're very easy to calculate by traditional analytical means. I'm not going to go through them, but I've left the equations there because I know this is being recorded and will be available later, so people can look this up later if they want. But the important thing to say is the pipe parts of the resistance are quite small and they're quite easy to calculate by standard methods. The more interesting bit is the resistance of the concrete part of the pile. And here, really the best way to go about this is to consider the multipole method. Now, this is an analytically precise method that assumes each pipe in the pile or in any ground heat exchanger acts as either a line heat source or a multipole, where a multipole is a complex number version of a line heat source. And the more orders of calculations you make, if you do the nth order multipole, then you'll have a more accurate result than if you use the first order or the line source. The more pipes you have, the more difficult this computation is. But luckily for us, just 2 weeks ago, our colleagues in Lund, Johan Kleisthen and Sakib Javid, published a new simplification of this approach for energy piles using the line source approach. So literally really hot off the press. This is the equation here. So it's the first closed form analytically precise equation to calculate the resistance for energy piles. So it's a major advancement just come out. And the important things I want to point out about it are that the resistance is dependent upon this value n, which is the number of pipes installed in the pile. lambda c, which is the thermal conductivity of the concrete, RB, which is the radius of the pile, and RC, which is the radial coordinate of the pipes, i.e. how far they are from the center of the pile. And it's also dependent on this parameter sigma, and sigma depends on the thermal conductivity of both the concrete and the ground. So the first thing to say is that the resistance depends not just on the thermal properties of the pile, but the medium in which it's installed. And the reason that is if you look at this example of a pile which has got 2 heat transfer pipes installed in it, you'll see that the heat flow is not purely radial. So the temperature around the circumference of the pile is not constant. So the heat flow is affected by the ground properties as well as the pile properties. And we can have a look in a moment about what this equation means, but the key points, if you like, are if you play with that equation or you look at any of the previous analysis on pile resistance, you want to minimize that pile resistance to maximize the energy efficiency. And to do that, you want to install as many pipes as possible within reason, and you want to put them as close to the edge of the pile as possible, i.e. as close to the ground. In an ideal world, you would use high conductivity materials for the concrete and for the pipes, but it's not always straightforward to do that practically. So, concrete aggregate choices are often about what is available locally, your local quarry or source of recycled aggregate. And it's not always straightforward to deliberately choose to use high conductivity materials. The other thing you can do is maintain turbulent flow in the pipes. Now, typical values of resistance for piles would be 0.05 to 0.3 meter Kelvin per watt. You can compare that to some typical values for traditional borehole ground heat exchangers, and you will see that the lower range for piles are more efficient than your typical borehole, but the upper range are less efficient. And this is all because you have so many more options about your geometry, because you have a bigger pile in which you can choose how many pipes and where to put them and things like that. So I'll just show you the impact of some of those things. In the top left, we've got the thermal resistance against the number of pipes installed for a 600 millimeter diameter pile. And if we look first at the blue line, you can see that as you increase the number of pipes, you can approximately halve your thermal resistance. If you then increase the conductivity of the concrete, you can drop down from the blue line to the orange line. So those are two things that are really easy to deal with. It's also worth observing that the resistance here against the pile radius doesn't really change if you don't change the number of pipes. So if you just have a constant number of pipes, but you increase the pile size, it doesn't really make much difference to the thermal performance. What really makes a difference is maximizing the pipe installations. And then at the bottom here, we've got resistance against the concrete cover for a 600 millimeter diameter pile with 4 pipes installed. So typically for a rotary pile would be down here. We'd have 75 millimeters of cover to the steel, and the pipes would be attached to the steel. If we increase that cover significantly, i.e. if we come up here to what would be a CFA arrangement where the pipes are in the center, then the resistance is much, much higher. And this is where the high values of resistance on the previous slide came from. So one really clear thing to say is that a typical rotary arrangement of pipes, i.e. where your pipes run the steel cage, is much more energy efficient than what in the UK would be a typical CFA arrangement with the pipes in the center of the pile. You might look at that and think, well, why are we even building those CFA energy piles? The answer is an energy pile is better than no energy pile, right? If you can use your foundations of your building to deliver renewable energy, you should be doing it full stop. So in an ideal world, you want to put the pipes on the edge, but sometimes our construction process gives us constraints about what we can achieve, and we just have to work with those. The final thing that it's really important to say about resistance is that it's a steady state concept. So this chart shows the percentage of that steady state that's achieved with time for a number of different pile geometries. And you will see that actually it takes a number of days for a steady state to be approached in a pile. And the reason this is important is because when you're operating your heating system of your building, the timescale on which the thermal demand fluctuates, is of the order of hours to half a day. So you might turn your heating on in the morning and turn it off at night. So if you're in here somewhere, your piles may be at 80 to 90 something percent of thermal steady state. So one of the common design assumptions that the pile is at a thermal steady state is not actually technically true for energy piles. It's kind of getting there, but it's not totally at steady state, and that does have an impact on the thermal behavior, which I will show you as we go on. But in the meantime, it makes sense now to talk a little bit about the temperature change that's happening in the ground around the pile. So I showed this slide before, and what I'm going to focus on in this section is this expression here, where we're trying to predict the temperature change at the edge of the pile, TB, according to this relationship with the heat transfer rate Q, the thermal conductivity of the ground, and this function G. So effectively, in the next slides, I'm going to be giving different definitions of this function G, and I'm going to give them in terms of a step response. And by that, what I mean is we're going to look at this function in terms of the temperature change that occurs with time for a constant thermal demand application. Now, as I've just said, in reality, building energy systems don't operate in terms of constant demand. Heating demand is forever being turned on and off, increasing, decreasing, often on hourly or half daily time steps. However, first thing we need to do is define this step response, and then we can use temporal superposition to deal with the fact that the demand changes rapidly with time. I won't go into details about that today because I want to focus on the fundamentals of the thermal behavior, but it's again a fairly standard approach that will allow us to deal with the fact that the thermal demand varies all the time. So I'm mainly going to talk about this function, this G function, how temperature changes with time for a constant application of thermal load. And there are a number of traditional simple models that can be used for this and have been applied routinely for the design of other types of ground heat exchangers like boreholes. The most common is the infinite line source, or the ILS, where you assume that your heat exchanger, your pile, is infinitely long and infinitely thin, which we know it's not, but we'll see it's actually a surprisingly good assumption. An alternative is to assume our heat exchanger, our pile, is still infinite in length, but it's cylindrical in shape, and the heating is coming from the outside of that cylinder, so that cylinder's hollow, if you like, and that's a model which is sometimes used. And finally, the most complicated of the three on this screen is the finite line source, where again we assume our pile is a line, but we take into account the fact that it has a finite length by having a line heat sink and a line heat source, and a mirror at the ground surface, which we assume is a constant temperature. And all these solutions can be developed analytically. The reason it's important that they can be used analytically is because, well, I guess there's two reasons really. One is that we have to apply this temporal superposition for the fact that our thermal demand varies. We also have to apply spatial superposition. So we're rarely dealing with just one energy pile, right? We're dealing with a group beneath a column, or several groups beneath several columns, or arrangement of different sizes and locations, and we have to take that into account. So we need something that runs fast. And we need something that runs fast and is easily accessible, because often a lot of design for ground energy systems is done by SMEs. And whilst numerical simulation allows us to pretty accurately model these types of ground heat exchanger, it's beyond the reach of a lot of the companies that are involved in doing this kind of work. And it's computationally really quite expensive as well, because you have to capture very small changes close to pipes, but also very large scale changes over tens of meters away from the piles. So these common analytical models are implemented in a number of bits of standard software that are readily available. Of them, the infinite line source is particularly attractive because it's really, really very simple. The G function here can be written in terms of the exponential integral, EI, the radius of the pile, the thermal diffusivity and the time that's elapsed. And you can evaluate that integral in MATLAB or things like that. But actually, if you expand the integral and you make an assumption about sufficient time period having elapsed, you come to a log linear solution, which is even easier to implement, and anybody can do it in a spreadsheet. However, all these three methods have some disadvantages for piles, which I'm going to go on to explain. So I'm going to do this by looking at this plot. So this graphical representation of the G functions. It's dimensionless time against dimensionless temperature. The units don't really matter. It's the shape of the curves that I'd like to talk about. So the first thing to illustrate is this straight black line here, which is the simplified log linear version of the infinite line source. In this approximation, because the heat source is infinite, the temperature change theoretically carries on ad infinitum for as long as time is running. So if you are continually extracting heat from the ground, the temperature change will just carry on increasing and increasing. And we know this is not right. This doesn't happen because we have the ground surface and because we have the finite length of the pile. If we assume the ground surface has constant temperature, this is going to limit the amount of heat that's available for us to extract, as Marcelo mentioned earlier. So in these cases, what happens is this curve actually rolls over and reaches a steady state, and exactly what time and what temperature value the curve rolls over and reaches thermal steady state depends on the aspect ratio, the length of the pile divided by its diameter. So aspect ratio 50 meter deep pile, 1 meter diameter, rolls over here. Aspect ratio of 15 rolls over here. So the shorter and fatter the pile, the sooner it reaches steady state. Now, actually, what happens with real piles is they're installed beneath buildings. So they probably don't have a constant temperature at the ground surface. They might have an insulated boundary condition at the top surface, or maybe the building itself will lose some heat to the ground. So actually, real energy piles probably plot somewhere between these lines. So that's the long term. If we go and look at the short terms, we've got our straight line for the simplified infinite line source here. This upper black curve represents the infinite cylindrical source model. And if we look at the red and the purple curves, these are more typical thermal behaviors for energy piles. So they sit somewhere between the two. And actually, really interestingly, it's not shown on here because there's not quite space, but if you implement the exponential integral version of the infinite line source, it also sits in here, in between the red and purple lines. So it's a surprisingly good model for the temperature changes in the ground around an energy pile. However, what happens in reality? I'm going to take a quick look at the overall response. So previously we were looking at the temperature change that happened at the edge of the pile. Here is some real data of the temperature change in the fluid for an energy pile against time when constant heating is applied. And the black slightly wobbly line in here is real field data. And next to it are some thinner green and kind of brownish lines. And they're what happens if you simulate this experiment with numerical models in 2 or 3D. You can get a pretty good match, as I say. These things are totally possible. It's just computationally very expensive. If we now compare what happens if we apply our simple models, here is the simplified log linear version of the line source, and that plots well underneath the real data. Here is the exponential integral version of the line source, which puts above the real data. Now hold on, I just said on the last slide that this model plots in the typical region for energy piles. So why is it above the data? Well, it's above the data because here we're dealing with the temperature of the fluid. And this model has been coupled with the steady state resistance concept that I mentioned previously. And that's why it's not capturing this early time thermal behavior, because it's assuming a steady state in the pile. So actually, when you look at the pile and the ground together, you need to consider the pile to be transient to get this short-term behavior right. And we've been working on that recently with this red dash line here, which is something called the Kleisthen Radial model, which assumes transient behaviour in the pile and in the ground simultaneously. I'm going to tell you a little bit about that in a moment. What I will just say is it's not bang on either, but it's doing a better job than the other models. It probably doesn't matter that it's not perfectly bang on, because there are lots of other uncertainties in the energy pile system. And one of the things that's probably even more uncertain than the ground parameters is what the thermal demand of the building is. So just to quickly say a few things about the Kleisthen-Javid radial model. In this model, you take typical geometries of an energy pile, be they a rotary pile like this or a CFA pile like this, and you assume that we can represent them as effectively a donut, like one equivalent single pipe to represent all the pipes and a donut shape for the concrete of the pile. So we can have purely radial heat flow, which is much easier to analyze. You end up with an equation that looks like this. I'm not going to go into how you can solve it, but there's full details in the reference below, and we have a paper coming out shortly which will give you more explicit instructions about how to implement it. But the main thing I wanted to say is we have now, in the last year, tested this model, which was developed for borehole heat exchangers for a wide range of pile geometries, and we think it works pretty well under a reasonable range of conditions, and is probably the sort of approach that we need for designing energy piles. So quickly to summarize the things we need to think about in the thermal behavior of piles. We need to get the ground surface boundary condition correct. Probably ideally insulated, but if we assume our pile is infinite, we get a conservative result. We need to think about the detail within the pile and whether we can make do with a steady state assumption. Really, we should be using transient if we can. Surprisingly, the classic infinite line source solution does a remarkably good job for the temperature change in the ground around a pile. But because it's infinite, it is conservative in the long run. And if you couple it with a steady state resistance, then it becomes conservative in the short term as well. And at some point you have to question how much conservatism you can take, because if you have too much conservatism, then people look at the energy calculations and go, well, that's not worth it, we're not going to do it. So really, it's better to have a model which is transient in the ground as well as in the pile. I want to quickly say something about thermal testing before I conclude, just because this is something that people might get asked to be involved in. So an in situ thermal response test is, it's analogous to a groundwater pumping test. You are circulating heat through the system and you are trying to work out what the thermal conductivity of the soil is to use in design. You apply constant heating power for several days. And important assumptions for the test are that it's a thermal steady state, which you've seen I've already questioned, and that we can interpret it with a line source because the heat flow is radial, which again potentially has problems. Because piles are larger diameter than boreholes that this test was developed for, we have to run them for a longer time to get over the heat capacity of the concrete because of this steady state factor. This means we have to use a lower heating power to stop everything overheating. This means that we get a smaller rate of temperature change with time. And this means that we can get a fluctuation in the thermal conductivity we calculate at large times, as shown in this chart here, thermal conductivity against time in the test. We run a longer test, we get fluctuations at the end. This is because we get ambient interference with the ground surface, with the air temperatures, and we get a decrease in the signal to noise ratio with time. The other thing that happens when we run tests for a long time to overcome the pile heat capacity is there are model errors. So I showed this chart before. Between these red lines is the typical time of a thermal response test, and we're fitting this straight line model to it here, but actually our results are probably one of these curves underneath that are kind of purple colored. So you can see we're fitting a curve at the wrong gradient basically, so we get model errors. And I can illustrate that by showing you some comparisons of field data against laboratory data for thermal response tests. Some of these are in boreholes and some of them are in piles. These ones in red circle are in piles. You can see there's a systematic overestimation in the field compared to laboratory testing when you test energy piles in the field. So you really have to be quite careful with this technique. I would say proceed with caution for thermal testing of energy piles, especially with large diameters. And don't plan to do a test unless you have got a more sophisticated interpretation method. So the line source method has a lot of drawbacks for testing of energy piles. You can get really good results interpreting them if you use numerical methods, or for example, if you use the Kleisthen Radial model, which I mentioned before, but you need to be prepared to do that extra analysis. And it might actually be much more practical for real projects to consider testing a separate borehole, either at site investigation stage or a special purpose borehole earlier in the construction program, particularly as actually, you know, testing of working piles can be on the critical path on the construction program. So there are many disadvantages with testing a working pile. It's not impossible. It can be done and it can be interpreted well, but you have to be really careful with it. So you'll be pleased to know that I'm going to sum up now. I just want to give you a few key messages that you can take away if you're thinking about energy pile projects in practice, or it's an area of research that you want to get involved in. The first thing to say is it works. We can successfully use energy piles as part of a system for transferring heat, delivering heat, storing heat in the ground. We can do it for any type of pile, pretty much. In different parts of the world, people have tried pretty much everything, and it works. If we want to maximize the efficiency of our system, we want to install as many pipes as we can, reasonably speaking, and make them as close to the pile edge as possible, i.e. put them on the pile cage, steel cage probably. If you can, use high conductivity materials, but it's potentially difficult, we appreciate that. There are existing methods for design of other vertical ground heat exchangers like boreholes, and we can apply them to piles with care, with some adjustments, but we need to account for the fact that the pile is transient, and we need to think about what happens at the surface of the pile. And while we can thermally test piles, we need to be quite careful about that as well, and how we interpret it. Things we need to think about for the future. I think we could still do with a fast runtime analytical approach that both accounts for the transient nature of the pile and for the fact the pile is beneath a building. I don't think we're quite there with that, although we're making progress. More field data is always really useful. I've worked to instrument a few sites now, and it's really difficult to get good field data. Requires a lot of collaboration with all the parties involved for a long period of time. And I kind of briefly mentioned it along the way, but we need to think about energy piles as part of a whole system. They're really dependent on the building as well as what happens in the ground. A lot of people working in energy piles think a lot about the pile, but don't think enough about the whole system. Just finally, I've got 2 more slides. I need to acknowledge the people who have been good enough to pay my salary and pay for my research in the last 10 or so years, the Royal Academy of Engineering and the Engineering and Physical Sciences Research Council in the UK. And also some of the things I've presented, you know, have been done in collaboration with a number of people, both in Leeds, where I work now, Southampton, where I worked before, and collaborators in Sweden and in Australia. So thanks to them. And also just to say, because I know these slides are going to be available later, I put a load of references up. You're not going to read them now, but it's for future reference, really. But I'll finish there, and thank you very much. Any questions?
So does the groundwater under natural convection affect the time for TRT?
It doesn't so much affect the time, but it does affect the results. So a lot of the design and the testing and all the analysis related to ground heat exchangers typically assumes that you have homogeneous and isotropic ground conditions, which as geotechnical engineers, we all know is not true, right? There are situations in which we assume average properties all the time, but groundwater is probably one of the big ones for shallow geothermal energy in general, because it's an additional heat transfer mechanism. You're basically adding a forced convective process in the ground. So what I would say about thermal response testing is if you do a thermal response test and you interpret the results transiently, so you work out a thermal conductivity with time, if your test is affected by groundwater, you will see that the thermal conductivity increases steadily with time during the test. So that's a killer indicator, if you like, that there is groundwater there and it's additional heat transfer process happening that you haven't otherwise accounted for. It doesn't mean you need to run the test for longer, but it means that the conductivity value that you calculate is really just an effective value that also includes the influence of groundwater. So you need to use your engineering judgment about what is an appropriate method, appropriate value, sorry, to assume in design. It's like a lot of things to do with groundwater. Do you want to assume that you can rely upon that flow for the lifetime that your structure is in place? Or could it be affected by somebody constructing a basement next door or something like that?
Another question comes to in regards to the application of energy piles, and the question is that what is the typical range in the temperature changes from summer to winter in the regions where you have seen the installation of this energy piles?
Yeah, I mean, it shouldn't be more than, 15 or 20 degrees or something like that. I mean, I would expect it depends a bit on the existing ground temperature and the thermal demand of the building, whether it's heating dominated or cooling dominated, but your system shouldn't really be operating more than 30 or 35 degrees at the upper bound, and it shouldn't really be operating less than, a few degrees at the lower bound. So a typical system is probably operating in a range less than that. It's really not a big range compared to some other energy geotechnics applications.
And how do you think that the permeability of the soil kind of affects the heat energy on pile?
Yes, so the higher the thermal conductivity of the ground, the higher the heat transfer rates that you can achieve. You're going to get higher thermal conductivity conditions if your moisture content is higher, because water has a higher conductivity than soil minerals. So higher porosity is good as long as you're below the groundwater table. Obviously, if you've got air is a really bad conductor. And as I've mentioned already, movement of groundwater is really positive for heat transfer.
Actually, I reply towards my idea is that suppose say I want to get in terms of strength. Once I'm inserting so many pipes inside the pile, am I compromising the strength, the load capacity of the pile?
So the pipes are typically something like 25 millimeters in diameter. So if you had a 600 millimeter diameter pile and maybe you installed 6 or maybe 8 pipes in it, might be typical. The cross-sectional area of those pipes compared to the whole of the pile is not a big issue at all. So I really don't think that should be a problem at all.
So in that, suppose you said if it is close to the cover is less, it's better.
Yes, cover is the smaller the cover to the pipes, the better the heat transfer. Now, yes. You've got to think about other engineering issues as well. So I know that Duncan Nicholson et al. in AGERP in London had a long think about this, because they were initially concerned, or they wanted to check what would be the impact of putting the pipes in the cover zone to the steel, because obviously you don't want to affect the protection given to the steel by the concrete cover. And therefore, whether you can have the pipes on the outside of the steel or whether you need to have them on the inside of the steel ring in order to protect the steel. And they convinced themselves that they were happy from a structural perspective to have the pipes on the outside of the steel cage. You do need to have something that you're attaching the pipes to get them in the hole realistically. So, it's going to be much harder to get them right at the edge. So the kind of practical solution is to put them on the outside of the cage, really, and then they are going to be within 75 millimeters of the edge of the pile.
One of the questions is also that how do you use these energy piles for heat storage? Can we use them for heat storage?
Yeah, the most efficient way is to use them in a balanced system. So a lot of, certainly in the UK and probably in a lot of the rest of Europe and North America, the energy demand of the sorts of commercial buildings that are going to have piled foundations is going to involve some heating and some cooling, because we all use too many computers. So there's definitely a cooling demand in the summer, and there's definitely a heating demand in the winter. So really the most energy efficient way to use the system is to cool the building in the summer and put that surplus heat in the ground around the piles and in the piles, and then in the winter to take that out to heat your building. It really is the most efficient approach. For any of these types of shallow geothermal energy system, you can get natural recharge as well. So if you just have a heating only system, say you have micropiles for a house or something, you're only using the system in the winter. So there should be natural recharge from solar radiation, maybe less if it's beneath a building than if you're if you're open to the ambient conditions, but you should be able to get natural recharge to so you're effectively storing solar thermal energy.
You mentioned about the large and the small piles. Can you give us an idea about what diameters we are talking about? What is large?
Yeah. So 300 millimeter diameter piles are definitely small diameter. They are probably reasonably sensibly modeled with a steady state thermal resistance without too much error. By the time you get up to 450 millimeter diameter, that's starting to get a bit marginal. And certainly by the time you're at 600 millimeters, then you're very much a large diameter.
What about the thermal exchange between the pipe skin and the steel when pipes are circulated around the cage of the pile?
Yeah, that's an interesting question, but it doesn't seem, as far as we can tell, to be a significant issue. We've done some, we have some field data, and also we've done some numerical analysis. I don't think the steel is a massive issue.
So this one is a general question. That do you really think that the natural convection really increase the power output?
Yes,
okay.
Definitely. You can see it, as I say, if you do a thermal response test and there is significant groundwater flow, you will see it. You will see it in the results, and there have been numerous numerical studies for all sorts of different energy geostructures, not just piles, but walls and tunnels, particularly work coming out of colleagues in Torino in Italy, that show that you really get the best heat transfer rates when you have significant groundwater flows. So they're particularly interested in that in Torino because they're in the plain of the Po River and they have significant groundwater flow. So yeah, it does make a really big difference. The main question, as I say, you have to ask yourself is, are you happy you can rely on that flow for the design life of your structure when you're making your calculations? Thank you, it's my pleasure. And yeah, please just get in touch if you want to know any more.